the trick, isn't it? No, maybe not. Maybe further away.
Okay.
Yeah.
Is your camera on?
So, I get.
Well, welcome everybody. We'll just give it a couple more minutes for a few more, to allow a few more people to join in. So we'll start in about a minute or two.
Good morning, everyone. Thank you for joining our session today, an introduction to the concept of Earth orbits. It's for the Astropreneur program. My name is Sue Davies, and I will be the session chair for you today. And I just want to run through the etiquette, the Zoom etiquette with you. You'll note that everybody is on audio. So please make sure that your audio is muted. A question and answer session will be directed at the end of the speaker slot. And if you can please use the chat function where we will pick up your questions. And if you have any technical issues, you lose the signal for any reason, just log off and log back on again. So I'm going to stop sharing my screen now and hand over to Nick Trick, who is the head of the Astropreneur program. Nick.
Good morning, everybody. Thank you very much for joining. This is our, I'll just share my screen. Brilliant. So this is our fifth in our series of Space Plus One talks, just a series of talks about space and related items or related subjects. Previously, we've done space and agriculture, space technologies in sustainable finance, space in government or used by government, and manufacturing in space, in and for space, actually. Those talks are available if you're at all interested, so please contact me if you are interested in listening to those. Today, we have John Davis from the ATC, the Royal Observatory in Edinburgh, part of STFC, who will give us an introduction talk about orbits. But before that, I just wanted to explain to you about the Astropreneurs program. Some of you already know about it, of course, but this is a Horizon 2020 funded project supporting space-related startups for with mentoring and training. And the objective is to help these become viable businesses and obviously grow this sector. The partners running this program are scattered around Europe. There are 8, led by the Instituto Pedro Nunes in Portugal, If you are interested in talking to anybody about the program, then please contact any one of those companies. They all count, and also, of course, you don't have to come from one of those countries. You can come from any one of the Euro 28. The more detail, of course, is on the website, the astropreneurs.eu. The mentoring program lasts a period of about 6 months and is valid for any organization's early stage startup with any space connection, so downstream, upstream, hardware, software, sort of anything you like, really. As I said, it's very early stage, so it can be even pre-incorporation of a business, so it's just an idea. The program to date has helped, or is helping, 160 astropreneurs across the continent, with an interesting split, you know, a quarter upstream, 3/4 downstream, and 1/3 hardware, 2/3 software. And really across the full range of industry sectors, or if you look at the industry sectors from the SIC code perspective. As I said, if you're interested in finding out any more of that about the program or some of the organizations on the program, please either contact me or anybody else in the organization, or go through the website. Thank you very much indeed. I'll stop sharing, and I'll pass over to John Davies from the Royal Observatory, Edinburgh. John. Yeah, that looks good.
You're on mute, John.
Right, I don't know what happened there.
We can
Okay,
hear
we can
you now,
hear
John,
you
and we
now.
can see your screen.
So my name is John Davis. I'm an astronomer at the UK Astronomy Technology Centre at the Royal Observatory, Edinburgh. I'd like to start with a little bit of what you might call expectation management. This presentation was prepared by me as an astronomer for a series of lectures we did at work to our engineers, the idea being to give our engineers some general background of topics slightly outside their area, so that if they were involved in writing proposals or helping or something like that, they would have some background. So this is a very basic introduction to orbits for satellites, particularly for astronomy satellites, but it's also got some stuff about non-astronomy missions in. I should say I'm a user of satellites, not a builder of satellites. So I'm speaking as someone who's worked at the ground station, as someone who's helped to build bits for astronomy satellites, but I'm not actually a spacecraft engineer in myself. I'm simply a user. So I'll start with a few very basic concepts, just to get us all on the same page, and then I'll look at a series of different operational orbits which you can use for various kinds of missions, not just astronomy, but obviously with some bias towards astronomy. So the first question is, where does space actually begin? And there's a number of definitions of this. The United States Air Force uses an altitude of 80 kilometers, or actually being America, 50 miles, which just happens to be 80 kilometers. And you know, cynically, you might say that's because that's an altitude which could be reached by their X-15 rocket plane, which allowed a few of the US Air Force test pilots to be granted astronaut wings without actually joining NASA. A more widely accepted definition is 100 kilometers, which is the so-called Kármán line. This is the altitude at which aerodynamic control, the air becomes so thin that aerodynamic control is essentially impractical. It's not exactly 100 kilometers, but 100 kilometers is a nice round number. You can come across different definitions of this, but basically at the von Kármán line, you have to be traveling at orbital velocity if your wings are going to generate enough lift to keep you up. So at that point, you stop being an airplane and start becoming a satellite. And that's the target altitude of the Ansari X prize, which was the prize given to launch a passenger plane, a spacecraft capable of carrying passengers into space. And that's also the target for Virgin Galactica's space tourism altitude. So they will fly passengers above 100 kilometers, which will qualify them for astronaut wings. If you actually want to stay in orbit, you need to go higher than that. There's still quite a bit of air at 100 kilometers. So 150 kilometers, you can just about stay in orbit, but not for very long. So now I'm having trouble changing our slides. There we go. So just a couple of technical terms. We talk about the orbit of a satellite in terms of its inclination, which is the angle between the orbital plane and the equator. Its highest point is called the apogee, and its lowest point is called the perigee. If I was talking to my air cadets, I would say that if you want to remember this, apogee begins with A, and so does the word away. So apogee is the furthest away from the Earth. The inclination to the orbit, the angle between the orbital plane and the equator, and for a given launch site, you will get optimum mass into orbit if you launch due east, and you will finish up in an orbit whose inclination is equal to the latitude of your orbit. So this is a map which shows, I will leave it as an exercise for the reader to identify all of those launch sites. But this is a map of different launch sites around the world. If you want to shoot into equatorial orbit, which is where the big communication satellites want to go, then the nearer you are to the equator, the better. First of all, you get a little bit of a boost from the Earth's rotation. And secondly, you're already in roughly the right orbital plane, which is why the European Space Agency built its launch site at Kourou in South America. That's number 5 on this map. You've also got to consider, if you're launching eastwards, where your debris is going to land, because most rockets are disposable first stages. So if you're launching from Cape Canaveral, which is number 4 on this map, you can't launch interpolar orbit because your stages will fall either onto the landmass of South America. If you launch south, or if you launch north, they'll fall onto Washington, D.C., which is not an ideal situation. So American missions into polar orbits tend to be launched from Vandenberg Air Force Base, number 1 on this map, which is on the coast of California. Then their stage, if they launch south, debris from the rocket launch falls into the South Atlantic Ocean. If you want to, another alternative, you can launch from a movable platform. So for a short period, there was this San Marco platform, which was off the coast of Kenya, which is where NASA launched small scout rockets into equatorial orbits. More recently, you can use an air launch platform. So the picture shows Orbital Sciences Corporation's Lockheed TriStar dropping a Pegasus wing launch vehicle. Pegasus is a solid rocket booster. But of course, you can have any launch azimuth you want, because you can fly the airplane out over the sea, and then you don't have to worry about where the stages are going to land. Orbital Sciences Corporation have launched about 43 of these Pegasus launches. They have, I think, 2 left, which are uncommitted, but it's not clear if they're ever going to build any more. However, most of you will know that in the last week or two, Virgin Space, which is another branch of Sir Richard Branson's Virgin organization, tried to launch a liquid rocket booster by dropping it off a jumbo jet. This unfortunately didn't go very well. It released all right, but the engine shut down after a couple of seconds and the mission was lost. However, I've no doubt they will sort this out, and then you'll have another one of these launch platforms which you can fly from anywhere in the world, possibly Newquay in Cornwall's an identified takeoff point. And then you have this freedom of choice in your launch azimuth, because you can fly out in such a place that there's no danger of the debris landing anywhere important. So in Midsummer Night's Dream, William Shakespeare has one of his characters say that he'll place a girdle around the Earth in 40 minutes. But actually, that's quite difficult. In fact, it's impossible. So this diagram here, this table here, has the orbital height in kilometers and the orbital period. And you'll see that even at a height of 12 kilometers, which is still in the atmosphere, the orbital period is 85 minutes. So an orbit of 40 minutes is going to be impossible unless you're below the Earth's surface, which is going to create a series of technological challenges, to put it mildly. Anything up to about 1,000 kilometers, we tend to call low Earth orbit, and these orbits have periods of around about an hour and a half, so something between 85 and 100 minutes. As you go steadily further outwards, the orbital period gets longer until at 36,000 kilometers or thereabouts, you finish up in the so-called geostationary orbit. At this altitude, the orbital period of the satellite is 23 hours and 56 minutes, and that's the sidereal rotation period of the Earth. It's not the length of a day, because we measure our day relative to the sun, and in a day the Earth moves around its orbit slightly, but relative to the distant stars, the Earth's rotation is 23 hours and 56 minutes. So if you have an orbital period of that, then your satellite appears to hover over a fixed point on the Earth. You've got to take into account the atmosphere. The atmosphere is going to create drag, which is going to slow your satellite down. And as you lose speed, your orbit will decay and you will eventually re-enter and burn up. The atmosphere is not a very precise thing, because the atmosphere it doesn't have a finite cutoff. It just fades away gradually. And the height at which it fades away, or the rate at which the density drops, is very dependent on other things such as solar activity. So the atmospheric drag it's not a constant. It's not even a constantly variable. It's a constantly variable constant, because it depends critically on what the atmosphere is doing on that particular day. And if we go back a long time, you may remember the American Skylab space station fell down much earlier than expected, because solar activity puffed the atmosphere up and caused it to re-enter sooner than expected. So at 200 kilometers, you'll be lucky to stay up for more than a couple of weeks. At 1,000 kilometers, you can expect to stay in orbit for 1,000 years. If you get out to geostationary orbit, your orbit's basically stable forever, millions of year periods, because the atmosphere at that point really is negligible. There was a European satellite called Geostationary, which was a gravity mapper, which operated at a very low altitude, 255 kilometers. This was unusual in two respects. One thing, the satellite was streamlined, which you don't normally expect to find satellites being streamlined. But it also had ionic thrusters, so that as atmospheric drag tried to pull it down, the ion thrusters were used to maintain this otherwise very low orbit. But generally speaking, at 200 kilometers, you wouldn't expect to stay up for very long. We also need to consider the so-called the Van Allen radiation belts. These were named after James Van Allen from the University of Iowa. They were detected by the first American satellite, Explorer 1. And these are areas where the Earth's magnetic field traps charged particles, mostly protons and electrons, in a donut shapes mostly around the equator. They are particularly bad news for spacecraft, because the charged particles degrade solar panels, they degrade the electronics, they make damage detectors like CCD detectors, and may cause unwanted changes in computer memories, bit flips, as the electrons pass through the electronics. And they're not great for human beings either, because the radiation potentially can affect your DNA and increase your cancer risk. So the human-occupied International Space Station orbits below the belt, below the main belt, below the inner Van Allen belt. And it's a good place to, it's basically the Van Allen belts are a good thing to avoid. There is a region of the inner belt called the South Atlantic Anomaly, and the clue's in the name. It's over the South Atlantic, where the Earth's magnetic field is such that the radiation belt dips quite low, and this is called the South Atlantic Anomaly. We've got another, here's our ground track. This is the line which is directly below the satellite as it orbits the Earth. And if you plot that line on a map, you get this classical S-shaped figure, which you've probably all seen from pictures of Mission Control in Houston. But it's important to realize that the orbital plane of the satellite is fixed in inertial space. It's fixed in space relative to the stars. The satellite doesn't care what the Earth is doing underneath it. So in a low Earth orbit, the ground trace appears to move backwards and forwards as the Earth rotates underneath the satellite. So what you get is this S-shaped pattern, which constantly shifts to the left or right, where the upper and lower bounds of the coverage are the orbital inclination of the satellite. So this is a satellite in an orbital inclination of something like 60 degrees, 65 degrees, because it's stretching up as far as Norway, but it's never reaching the poles. So this orbit is normally, in an ideal world, this orbit will be fixed in space and the Earth would rotate underneath it. So when I talk about space astronomy, and the first people's reaction is the Hubble Space Telescope. But actually the Hubble Space Telescope is in a very low Earth orbit, and it's, ironically, it's an awful place to do space astronomy. For one thing, the orbital period is 90 minutes, so it spends half its time on the night side of the Earth. There are frequent eclipses when the sun is cut off, which means there's no solar power. So you have to have large batteries to maintain the spacecraft operationally while you're on the night side of the Earth. And then as you come round, you have to rapidly recharge those batteries during the 45 minutes you've got of sunlight. You can't point your telescope at a target for any long period, because before long the Earth will get in the way. And this orbit is so low that normal half of the sky is blocked by the Earth. In addition to that, you have stray light reflected from the Earth, which again limits your pointing directions quite considerably. You have a high load of heat radiation because the Earth is quite warm. So on the one side, you've got the sun shining on the spacecraft from above, and the Earth radiating at it from below. And even when you get around onto the night side of the Earth, you've now cut off the sunlight, but you've still got a lot of thermal radiation coming up from the Earth, warming up your satellite. And this is constantly changing because your angle between the Earth and the sun is changing as you go around the Earth. So why on earth would you put the Hubble Space Telescope in that orbit? And the answer is, it is easily accessible. Now, I don't like to use the word easily when I talk about space, because there's nothing easy about shooting things into space. But the Hubble telescope was predicated on it being serviced by space shuttle astronauts. Actually, it was originally designed to be returned to Earth, serviced, and then relaunched. So it had to be reachable by the space shuttle. And the space shuttle itself is limited to low Earth orbit. So so that's why the Hubble telescope is where it is. These orbits are relatively easy to reach, so they're popular for Cubesats, lightweight satellites, because the launch costs are low. And you're mostly below the Van Allen belts, as long as you don't dip or climb into the South Atlantic and on. So I said that these orbits are fixed in space, and they would be if the Earth was round, but it's not. The Earth has an equatorial bulge, and it's slightly pear-shaped in addition to this. So the gravitational field of the Earth is not constant as you go around the Earth in orbit. And if you're clever, you can use these slight deviations from a sphere to use the Earth's gravity to gradually process the orbit of your satellite. So the orbital plane rotates around the Earth as the satellite goes round. And if you pick the right combination of height and inclination, you can tune these to get an orbital drift of about 1 degree per day. That's 360 degrees a year. That's a complete circle. So as the Earth goes around the sun, then the orbital plane will creep around, constantly tracking the sun. And this is what's called a Sun-Synchronous orbit. Here's an example of one. This is the IRAS satellite in which I worked in 1983, and you can see that the satellite is essentially constantly orbiting on the Sun-Earth line, so it's always got solar power on the panels, and the Earth is simply rotating underneath it. And to get an orbit like this, you need to be in an orbit which is just slightly past 90 degrees inclination. So 90 degrees would be literally passing over the poles. This is slightly more than that, slightly retrograde, and at an altitude of around about 800, 900 kilometers. And if you pick an orbit like this, you can keep the relative positions of the sun and the Earth and the satellite pretty fixed. IRAS did an all-sky survey in the infrared. This had not been done from the ground because of atmospheric absorption, and the satellite was cooled with liquid helium to a couple of kelvins. This made the telescope very sensitive, but it also limits the lifetime because the heat load from the Earth boils away the cryogen. So IRAS's lifetime was only 10 months. The other disadvantage that this orbit had was that it was controlled from the Rutherford and Appleton Laboratory in Oxfordshire, and our picture shows it flying over Britain. But it only had an 8-minute ground station contact. You only had 8 minutes to load up 12 hours worth of observations and get 12 hours worth of data back down again. And you got 2 or 3 passes. And if you didn't get a contact on one of those passes, then the spacecraft was blind for the next 10 hours until a future pass over Rutherford. So we used to talk to the spacecraft twice a day, and each time we had to give it 12 hours of instructions, and it had to operate by itself for the rest of the time. I don't want to get too bogged down in the IRAS orbit, but here's a diagram of it. It's on the Sun-Earth terminator. It's constantly looking outwards, so it's sweeping across the whole sky. And the satellite was pointed so that each orbital pass overlapped the previous orbital pass by 1/2 of the focal plane. So you would do this bit of sky, and then you would do that bit of sky. So every bit of sky got scanned twice at 90-minute intervals. This was important because IRAS was launched in the days before we had infrared detector arrays. The IRAS focal plane, shown here on the right of the slide, had a lot of individual detectors. And as the stars traveled across the detectors, each individual detector would light up for a brief second. And if it was a real detection, it would then light up again another detector a 1.5 seconds later as the image traveled across the focal plane. An 1.5 hours later, when the satellite came back to the same patch of sky, the star would follow a different path across the focal plane, and it would again light up 2 detectors. So you would see the things confirmed on a timescale of seconds, and then timescales of 90 minutes. And as the satellite pointing direction crept ahead of the sun line, they would flick it back every week or so and repeat the process. So we would reconfirm the sources on a timescale of a week. But by the time something got into the IRAS catalog, it had been seen 8 times, and we were pretty confident that it was real. Similar orbits are used by modern satellites, such as the Wide-Field Infrared Spectroscopic Explorer and the Japanese Akari spacecraft, but these have infrared detector arrays, so they don't need this complicated confirmation strategy, which we used on IRAS 40-odd years ago. So Sun-Synchronous orbits are useful for satellites missions which are surveying the whole sky, but they're also useful for satellites which, instead of looking up, look down. Because if you're in a polar orbit, then your orbit will take you over the whole of the Earth's surface sooner or later. And remember, the Earth's rotating underneath you. So the ground track repeats on a regular basis, and it covers the whole Earth's surface. This gives you a whole bunch of advantages if you're interested in using satellites for ground observations. But one thing, the ground trace repeats, and it always occurs at almost exactly the same sun angle. So that means that if you're using shadows, for example, to estimate the height of buildings, the fact that the satellite will always come over at the same time of day means that the shadows will be more or less the same every time, and it makes it much easier to see if things are changing. Buildings have been knocked down or new buildings have been built. It's reasonably low, so you get reasonable image quality, but you only get a few minutes of observation because you're flying over any individual point quite quickly. You have the same problem we had with IRAS, that if you have a fixed ground station, you only have a few minutes to communicate with it every few hours. But the altitude is low, so you don't need particularly powerful antenna. So these sorts of orbits are good for things where you want to see the same bit of the Earth at a regular interval in a constant way. So things like crop monitoring, urban planning, environmental studies, strategic military reconnaissance, i.e. has the bad guys built a new airfield. They're less good for something where you need real-time information because you only get those 8-minute passes that maybe repeat once a day or once every couple of days. So they're not much use for things like air traffic control where you need constant information. If you want more constant information from an orbit like this, then you need to use a constellation, which is multiple satellites in similar orbits, so that as one flies over, another one's coming. And that's the strategy used by Iridium, which was a satellite communications program. They put multiple spacecraft into multiple orbits, so there was always one in contact with a potential ground user, which was a cell phone user in those days. But it has a problem because, as you may know, about 10 years ago, one of these Iridiums hit a Russian satellite, the Cosmos, a defunct Cosmos satellite. And when you get a collision like that, of course, they're very high-speed impacts, and you generate a lot of debris. And the debris tends to continue roughly in the orbit that it was originally in. So as these two satellites collided and disintegrated, they produced clouds of debris, which then continue to orbit the Earth, continue to intersect each other, and so potentially can recollide. And they just add to the ever-growing population of dead satellites and miscellaneous space debris, which is occupying low Earth orbit. So there's each of these little circles, these little flying saucers, show the collision cross-section of other satellites, and you'll see that there's a real risk that once you've had one collision, the debris will then start to impact other satellites. And so space debris management, space situational awareness, knowing where the stuff is, and space debris management, how do we get rid of it, how do we minimize it, is going to be a bigger and bigger issue as we put more and more satellites into low Earth orbit. If we jump up a bit, there's not many things that operate in these sort of 1,500 kilometer medium Earth orbits, but one notable use of these is the GPS Navstar system. They have 24 satellites in 6 orbital planes, and the reason for this is that you've got to be able to see, if you want your position, this is what drives your GPS and your phone and your car. And if you want to get your position accurately anywhere on the Earth's surface, you need to triangulate to up to 4 satellites. So the orbital constellation has to be such that wherever you are, walking across the Sahara, bicycling in Edinburgh, sitting under the South Pole in a nuclear missile submarine, you have to be able to see 4 of these satellites at any one time to get your position. Look at that. If we go higher still, this is the so-called geostationary orbit. This is the altitude where the orbital period of the satellite is the same as the orbital period of the Earth, of the rotational period of the Earth. And a single satellite in a geostationary orbit will appear to hover above a fixed point on the Earth's surface. So those of you who have Sky TV, you have a little dish the size of a dinner plate, you point it at the satellite in the sky and nothing has to change because the satellite remains fixed in space. Now this sort of orbit is very useful for direct broadcast satellites like Sky TV, for Intelsats, telephone communication satellites, and also for the data relay satellites called TDRS, which is what NASA uses to communicate with satellites in low Earth orbit to replace the need to have multiple ground stations. If you have 3 of these satellites at 120 degrees apart, you can talk to anyone on the Earth almost instantly. And those of us who are old enough to remember this, you know, today we don't think anything about picking up a telephone and dialing somebody in Australia, but 50 years ago that was practically impossible. Geostationary communication satellites have completely revolutionized international telecommunication. But I'm an astronomer. I'm interested in spacecraft that can point at things in the sky for long periods. IRAS did a great job of mapping the whole sky, but it could only point in a single direction for 8 minutes. So if you want to go make long uninterrupted pointings, you need a different orbit. This is the European Infrared Astronomy Satellite, ISO, the Infrared Space Observatory, which I worked on back in the 90s. It's an IRAS-like mission. It's actually a 60-centimeter telescope sitting inside a huge bucket of liquid helium to keep it cold. But unlike IRAS, it's not in a low Earth orbit. It's in a highly eccentric orbit like this. It's essentially a stretched version of the geostationary transfer orbit, which you would use to put up your communication satellite. Now, this has a 24-hour period, and as the satellite passes perigee, it climbs up to about here, at which point it's clear of the radiation belts, and you can see it from Villafranca in Spain. It then takes about 20 hours to climb to its apogee and then gradually fall down again. And all of that time, it's visible to the ground station at Villafranca. So astronomers could communicate with the satellite continuously and make long pointed observations. The Earth's not in the way because it's a small angular size. Of course, as you plunge back into the radiation belts and you disappear behind the Earth, you lose contact from Villafranca, but you wouldn't want to be doing astronomy then anyway because the radiation environment would mess up your detectors. So these highly eccentric Earth orbits allow long uninterrupted pointings and communications for long uninterrupted periods with a single or a small number of ground stations. And similar orbits have been used for large X-ray satellites such as Chandra, which is the American X-ray Observatory, and its European equivalent X-ray multi-mirror / Newton. Both of these things are in highly eccentric, high Earth orbits, which allow long uninterrupted pointings and fairly continuous coverage with a small number of ground stations. There's one other kind of orbit which is worth a mention here, and that's the orbit operated by the International Ultraviolet Observatory. This had an orbital period of 24 hours, but it was not circular and it was not in the equator. So it was geosynchronous, but it wasn't geostationary. Its orbital period was 24 hours, but it didn't hover in the sky. And the bottom picture shows the ground trace. In fact, it loops in a figure of 8 over the South Atlantic. For 8 hours a day, it's visible from Spain, which is because this was a joint mission with the Europeans and the Americans. So the Europeans got their direct contract for 8 hours, and then for the rest of the time, it was visible from the United States. So the Americans could operate the satellite for the other 16 hours a day, and then hand back over to Villafranca when it was the Europeans' turn. So that's a geosynchronous but non-geostationary orbit. The Soviet Union or the Russians use a similar sort of orbit for communications. Because their main Russian launch site is at Baikonur, which is at 65 degrees, it's very difficult for the Russians to get into geostationary orbits in the equatorial plane. And even if you do, from northern Russia, the satellite is very close to the horizon. So the Russians adopted a different strategy. They put their communication satellites into a highly elliptical orbit with a low perigee over the southern hemisphere and a apogee over the northern hemisphere. So the satellite climbs up here and it becomes visible to ground stations in Russia, and then it takes many hours for it to transit across the sky from a Russian ground station. So you get many hours of continuous contact. You do have to track your antenna slightly, but it's not drastic because the satellite is moving on the sky fairly slowly. And just as one satellite starts to drop below the horizon, another one pops up from the other side. So then you swing your antenna across to the other side of the sky and follow that one for 8 or 10 hours. So that gives you, essentially, if you have 3 or 4 satellites in roughly the same orbit, you get long communication periods without having to go into geostationary orbit. And these orbits are sometimes called Molniya orbits because that was the name of the Russian communication satellite that first used this. Here's another one. It's a so-called Earth trailing orbit.
Excuse me, John. I'm just giving you a time check here. Thank you.
Yeah, right. Okay. So in this case, you launch the satellite just enough energy to drift away from the Earth and gradually falls behind the Earth as it goes around the sun. This gives you long uninterrupted pointing. It keeps you away from the Earth, so the thermal heat load is low because this was for an infrared telescope. But you do have the difficulty that as time progresses, the satellite gets further away, so it gets harder and harder to talk to. This orbit is also used by Kepler. Kepler is not a cooled satellite, but it's a planet finder, and it needs to point to the same piece of sky all the time. So you need to get away from the Earth, otherwise you have Earth-Moon constraints which stop you pointing. Now we in Edinburgh proposed an alternative method of driving an infrared satellite, which was to take all the cryogens out and let it cool by itself. We proposed a thing called Kourou and then reinvented it, called it Edison. This was a radiatively cooled telescope, so it didn't have any cryogens at all. The mirror was just allowed to cool down by radiation to space. And that will work a lot better if you get it away from the Earth. So we propose putting this passively cooled satellite into a Lagrangian L2, which is about 1 million miles from the center of the Earth. Here's a diagram. Every planetary system has 5 of these points. The L1 point is on the line between the Earth and the Sun on the inside, and so it's a good place to put solar monitoring satellites. The L2 point is on the Earth-Sun line, but on the outside, so it's a good place for astronomy satellites. Now, normally something at L1 would be closer to the Sun, so it would orbit faster than the Earth and it would pull ahead. Similarly, something at L2 would be further from the Sun, so it would lag behind. But as the L1 point tries to accelerate away, the Earth's gravity drags it back. Similarly, as the L2 point tries to get left behind, the Earth's gravity pulls it along. So these points are relatively stable. The L1 point is used for solar missions. The L2 point is used typically for astronomy missions. So L2 has a number of advantages for astronomy. The Earth, Sun, and the Moon are all on the same side of the spacecraft. So the thermal environment, the light environment is very stable. You only need one set of sunshades to keep everything cold. The Sun and the Earth occupy only a small fraction of the sky, so you can point more or less wherever you want. And even the area which is blocked by the Sun changes as the Earth goes around the Sun. So within a few months, any area which is obscured by the Sun will become visible. However, there's a downside. You've got to get a big launcher to get you there, or you have to have a complicated profile which involves multiple loops around the Moon to gain energy. The L2 point is not completely stable, so you do need a certain amount of thruster fuel to stay in position. And because you're more than 1 million kilometers from the Earth, you need a much more powerful radio system to transmit the data backwards and forwards. Nonetheless, it's been a popular place for satellites for astronomy. The two on the left are background radiation, experimentally in the cosmic radiation background, COBE and WMAP. This is Herschel, a pointed sub-millimeter astronomy telescope. This is Gaia, the Sky Survey mission, which is mapping the stars with very great precision. And down at the bottom right, we have the James Webb Space Telescope, which NASA will hopefully launch next year. This is a very large telescope. It's radiatively cooled, so the sunshade at the bottom keeps the whole thing cold. The mirror is 6.5 meters in diameter. Now you probably speak meters, but those of you who don't, 6.5 meters is about the size of the gable end of a detached house, two-story detached house. So this is a very large telescope. And in fact, it's so large, it has to be folded up to fit inside the launch vehicle of an Ariane 5 shroud. So that's basically all I got to say about this. There's a slide here which I'm not going to talk about because it's just there for reference if anyone downloads the PowerPoint. And finally, there's my pub quiz question, which is, I've talked about Apogee and Perigee. These are strictly only applied to the Earth because the G in Apogee is the same G that we use when we talk about geography and geology. Strictly speaking, if you're talking about an orbit around the Moon, you shouldn't talk about lunar apogee. There are in fact two words for this, perisyntheon and perilune, and the question is, what's the difference? And the answer is that perisyntheon is the closest point to the Moon for a satellite launch from the Earth, such as lunar orbiter here on the left. Perilune is the closest point to the Moon from a satellite launch from the Moon surface, which is, in this case, our Apollo lunar module ascent stage. And there are similar words like periapsis for Mars and perijove for Jupiter. So that's it. Talk's over. Lunch window will open soon, I guess. And that's me done. My final slide is just the credits. Photos mostly NASA and ESA, and the orbital animations were done by this tool from Analytic Graphics. I used the free version, but there is you can buy a license if you want to do more complicated things from it. So that's me done. Thanks for your attention.
Thank you very much, John. There is some questions, so let's get started.
Stop sharing my screen.
Yes, please.
There we go.
There are numerous companies proposing collecting debris and then deorbit it. They rarely seem to take into account of the vast distances and the fuel burn required. Do you think debris management is achievable, or is the future active management of existing spacecraft and an acknowledgement that some debris will just have to remain the reality, please?
I'm not an expert at this, but I tend to agree with your question. I've seen these satellites of fire harpoons and stuff like that. But it seems to me there's an awful lot of debris and it's very widely spread. And unless you had a particular reason for wanting to capture a particular piece of debris, for example, it was in an orbit which might clash with the space station, then I suspect a much better plan is to accept that, as you say, that some debris will stay in orbit for a while at least, but to actively manage new satellites so that they deploy solar drag sails or something to cause them to re-enter once their lifetime is over. And I know that some of the CubeSat manufacturers are building their CubeSats with little pop-out drag systems that can be used to accelerate their atmospheric drag and their re-entry. So while I see firing arrows and firing nets at satellites is very dramatic, personally, I wonder how practical it is.
Thank you. Where is the main growth area? Is it research, communications, military, or other?
Well, that's, I mean, that's something for your entrepreneurs, really. What I've seen in the last 20 years, particularly, is the amazing acceleration in CubeSats. I mean, I grew up in an era where satellites were the size of cars, and you launch one a year. Today, CubeSats are the size of shoeboxes, and you launch them dozens at a time. And I can see a lot of use for these things for downward looking environmental monitoring, that sort of thing, because it's quite astonishing what you can do with a 10-centimeter CubeSat these days. So my view is that it's downward looking stuff where the money's to be made.
Thank you, John. Do you need to protect the non-concentric orbiting satellites as they move through the Van Allen belt? If yes, is there a common method of how it's done? If no, why not?
I'm not quite sure I understand the question, but I mean, if it's a question, if the sense is, if you're going to have a satellite which is going to encounter the Van Allen belts regularly, then you have to harden your electronics to make them as resistant as possible to radiation. You can shield them with metal, but of course that's pretty heavy. So the use of rad-hard components, which are electronics specifically designed to operate in high radiation environments, is what you need if you're going to operate in the Van Allen belts. But I mean, a better plan is just not to operate in them, because it's very difficult to, particular solar cells. The solar cells will degrade rapidly with time if you're using solar cells for power.
Thank you, John. Do you have issues with asteroids when using the Lagrange points?
No, not really. There don't seem to, I mean, I'm an asteroid astronomer, as a matter of fact, and there are almost no known objects trapped in any of these gravitationally stable points in the Earth's moon system. There are a couple that have been turned up in the last few years, but they're very few.
Okay, thank you.
Because those orbits are not fully stable. Satellites like James Webb have to have about 0.5 meter per second of delta V every year just to keep them in place. So if a natural object wandered into one of these places, it wouldn't stay there very long, because the solar system is not a three-body. You know, it's not just the Earth and the Sun and the satellite. There's the Moon and there's Jupiter and there's Mars. So those orbits are not completely stable. So natural objects will drift away naturally.
Thank you. Is space getting too crowded? Should we worry that we will run out of space?
Well, people have become increasingly worried about that. The Iridium collision was 12 years ago now, but that was quite a major event at the time. And there was a near miss predicted only a few months ago, actually, funnily enough, with my IRAS, with the IRAS satellite, which has long since stopped operating, but is still in orbit. And that was the prediction was that the flyby distance would be tens of meters. So there was a potential collision there with another satellite. So I think people are getting much more aware of this risk. Whether or not we'll ever be trapped on the Earth by a solid wall of debris, I doubt, but it's something that people who operate commercially in space will have to think about very hard, because you wouldn't want your communication satellites or whatever to be suddenly disabled by a collision.
Thank you, John. And we have one final question. Why does the space shuttle have such big wings?
Oh, that's because the space shuttle was originally conceived in collaboration with the United States Department of Defense. In order for NASA to get the backing to build the space shuttle, they had to convince the American Defense Department that it could be used to launch spy satellites. Most spy satellites are launched from Vandenberg Air Force Base in California because they want to go into polar orbits. For all the reasons I said about looking over the whole Earth's surface and constant sun angles and so on. But if you launch from Vandenberg Air Force Base due south and you just do one orbit of the Earth, by the time you're back to the latitude of Vandenberg, the Earth has rotated underneath you and the launch site has moved 1,500 miles that way. So you have to, if you want to land back after one orbit, you have to have big enough wings to allow you to fly sideways across the Pacific Ocean. You don't have that problem if you launch from Cape Canaveral, because as the Earth's turning underneath you, you just have to fly on a little bit further to get back over Cape Canaveral. But if you're in a polar orbit, your launch site rotates underneath you. So in order to meet your requirements to launch from Vandenberg and to recover to Vandenberg in the event of a launch abort or a one orbit mission just to deploy some military payload, you'd have to have these big wings to get the cross-range capability to fly back through the atmosphere and reach the runway at Vandenberg and not finish up landing in the Pacific Ocean.
Thank you, John. Okay, that's the end of the questions. I would just like to say thank you very much. And the presentation and the recording of the session will be available after the session ends. So I'll pass you back now to Nick, who will close the session. Thank you very much.
Thank you, Sue, and thank you, John, very much. I thought it was absolutely fascinating. I was trying to think of something witty to say about the pub quiz question, about either not having pub quizzes or not remembering it, but I can't even pronounce the words anymore, so I'm still not the guy to answer that one. Although I am perplexed as to somebody coming up with such complex words for such esoteric things. Anyway, that was the last in our current series, our sort of spring-summer series of lectures from the Astropreneurs program. We're hoping to do a few more in summer-autumn, so sort of September, October, so please stay tuned for those. The details of this particular talk, the recording and the slides will be available or sent through to your registered email address that you gave when you registered for the talk, and but it will also be available on the astropreneurs.eu website shortly, as will the details for all of the other talks that we've just had recently. So just to remind you of those, if you are interested, that's space and agriculture, space manufacturing, space and sustainable finance, and space used in government. Lastly, thank you again, John. Really appreciate that talk. Thank you, it was fascinating. And obviously, thank you to all of you who've signed up and attended. Thanks again, and hope to look forward to seeing you again in September. Bye-bye.
Thank you, goodbye.